In this video, we will semi-Eulerize a graph to solve a street routing problem in order to find an Euler path in a graph. And so we're going to do the same exact graph where we've already figured out where the even vertices lie. So, where the odd vertices lie, of course. And that's always step one in a street routing problem, find the odd vertices. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Now the difference is if we're trying to find an Euler path, we want to make sure the starting and ending points are odd, as was indicated by Euler's path theorem. So if we're looking at this, it says to semi-Eulerize by finding a path starting from G and ending at J. So in our graph, let me make this a little bit bigger on my tablet so I can see it. We've got G here. So notice that G is odd, which is actually good in the case of an Euler path, because we have to start at an odd vertex. But it also says let's try to end at J. And notice that J is actually not odd. So really, J is actually a problem vertex here because it is not odd, and we want it to be odd. So when you're semi-Eulerizing, it's not just as simple as connecting all the odds together. Sometimes you actually need to make another vertex odd. But actually, in this case, in order to find an Euler path, I still need to connect all the odds together. But you don't want to connect all of them. You want to connect all of them except the start and the end point. So I connect all those two together, but I'm left with the problem where this one is odd, and this one is odd. Sorry, this is not a problem. We want this one to be odd, but this one is odd and we don't want it to be odd. And this one is, notice that J was our desired endpoint, but it is actually even. But what we could actually do here is we could connect I and J, which would Eulerize I, making it even, and it would actually make J odd, which is a necessity because of Euler's path theorem. So with semi-Eulerizing is a little bit more complicated because you want to connect all the odds together except the starting and end point. And in the case when the starting and end point are even, you actually want to add an edge to them to make them odd. And now we would say that this graph is semi-Eulerized because everything is even except the start and the end. And we've done that in an optimal, we've optimally semi-Eulerized this because we've used only 4 edges to do it, and there's no other way to do it with less. And once it has been semi-Eulerized, again, now we're ready to solve the problem. We're good to go to find our optimal route. So if we're starting at G, we could do the same exact thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm just speeding this up because we already really did this before. And that would give me 13, 14, 15, 16, 17. And notice that it works. That's the whole point behind even and odd, studying all the even and odd and doing all this. And that will wrap up our chapter 5 on Eulerization. So this chapter is typically pretty difficult, but if you've been watching all the videos, I think it's helpful in developing all the ideas from start to finish. And really, I'll just take this opportunity to summarize once again. How do you do these? Find all the odd vertices, connect them together, good to go, and that's basically it. So really, there's a remarkably simple solution to these problems, while the actual math that goes into it is quite complicated and there's a lot of it. So, focus on the big ideas. If you're a little bit fuzzy on the theorems and stuff in general, it's not that important, but if you can do this, that's really what we need to solve a street routing problem. And in later chapters, we're going to be using these graphs to do very different types of problems, but at the end of the day, we're still using graph theory and we're doing them. Anyways, that will wrap up chapter 5.